Okay, thanks very much. And I'd like to thank the organizers. It's great to be at this workshop. And I would like to talk about this don't work with Lee simply, as you, Andreas, is on the archive. So I'm going to tell you about a bunch of things. So first I'm going to start with the basic setting, encoding qubits into qubits. Then I'm going to talk about encoding d-dimensional systems into oscillators and then oscillators into oscillators. So let's start with the basic setup. We heard about this in Matthias Christopher's talk. So basically we're assuming some single qubit noise channel which acts in IID on a physical qubit. And to protect against this, a unitary encoding map on several qubits, and this space defines a subspace of an n-qubit which an error encode. In addition, we have a recovery map that we try to recover from this noise. Now, very often this recovery map actually maps you back to operators that are supported on this code space. In this case, there are logical error operator, CPT map, that sort of makes this entity true. So basically, so if you have a situation, you can basically say when this error correction is beneficial. Essentially, it's beneficial if the logical is weaker than this physical, and you can measure this, for example, using the diagonal norm distance to the identity channel. Now, what do we mean by a threshold? When we talk about threshold, we usually mean a family of codes, perhaps indexed by the number of physical qubits, and each of these codes encodes k logical qubits. So basically, we just scale up this number of ancilla states in the encoding, and what we want is that we can make this effective logical noise arbitrarily weak. And this is usually the case as long as this physical noise rate is below some threshold value. And this is why it's called the threshold theorem. So if this is the case, we can find some code with maybe lots of qubits, such that this effective logical noise is very weak, weaker than any value epsilon. And as you will know, this can be done, for example, using stabilizer codes for natural error channels. Okay, so let me now get to the next point, which is encoding qubits into oscillators. And I'm going to use standard terminology for N bosonic systems. So we have canonical mode operators, Q and P, and these satisfy canonical commutational relations. And when we exponentiate linear combinations of them, we get so-called displacement operators, which satisfy these Weil relations. Now, I'd like to point out that two such displacement operators, they commute if and only if the symplectic inner product of the corresponding vectors is an integer. So we also say that these two vectors are symplectically integral together. This is important because we're going to define code spaces as the eigenspaces of commuting operators. So here's the construction by Gottesman-Kitaev and Preskill. You take two n linearly independent vectors, which are pairwise symplectically integral. And so in other words, you have a bunch of commuting displacement operators. And now you define your code space as the simultaneous +1 eigenspace of these operators. Now, in fact, I should be a bit more precise here. These are not actually states, but in fact distributions, and you can look in this paper for a mathematically rigorous treatment of these objects. For the purpose of this talk, I will just pretend these are states. Excuse me. Okay, so let me say a few things about these code spaces. So one thing you can do is you can multiply these displacement operators associated with these vectors, and that corresponds to adding these vectors. So you generate a lattice using these vectors, and this is the so-called stabilizer group of this code. Now, associated with this lattice, there's a dual lattice where duality is defined with respect to the symplectic inner product. And this dual lattice is important because it determines properties of the code. So for example, the dimension of the code can be computed as this expression. So it involves this ratio of the volumes of the unit cells of these two lattices. And logical operators in this code correspond to displacements that are associated with this Cossack group of this dual lattice modulo the original lattice. Okay, so let me make this a bit more concrete using the standard GKP code. So here we start with these two basis vectors of the lattice, and the dual lattice turned out to have half the lattice spacing. So the ratio of volumes is 4. If you take the square root of, you get the two-dimensional encoded space. So this encodes a qubit. And what you can also see here is that displacements by this amount correspond to logical X, Y, and Z operators on this encoded qubit. Okay, so now I have to explain how you actually do error correction with these codes. So let's assume we have a state which is encoded in this GKP code. We know that it is stabilized by these displacements. So these are the stabilizer operators. Now, the kinds of noise channels that we're interested in here are classical displacement noise. So let's say we have a Gaussian distribution with variance sigma squared, and we displace in phase space according to this Gaussian distribution. So if you do this to every mode, the overall error is a random displacement determined by some 2n variate Gaussian vector y. Okay, so to recover from this noise, we're basically going to measure the stabilizer generators, or equivalently, you can just measure the exponents. So these turn out to be commuting operators. So Q and P don't commute, but Q modulo square root of 2 pi and P modulo square root of 2 pi commute and can be measured. And when you measure this, you actually get a syndrome which depends deterministically on this displacement y. And once you have this syndrome, you are going to compute a correction vector. And the decoding strategy that we're going to consider in this talk is the following. So basically, we just do maximum likelihood decoding of the physical error. So we're trying to, we're looking for the error that's most likely given this observed syndrome. And then we just take minus that vector. So in other words, we apply the inverse displacement, and we try to map back to the code base. So this is the recovery strategy. And let me now also illustrate this. So we are the lattice, the dual lattice, the Voronoi cell of the dual lattice here. So let's assume we have an error vector, a displacement by some vector y. Then when you measure the syndrome, basically you get is this vector here. So this is sort of the modulo dual lattice reduced vector. And given this vector, you can now ask what is the most likely error given the syndrome. And if you assume a centered Gaussian distribution, then the most likely error consistent with this syndrome is just given by this vector. So if you take minus that vector, that gives you the correction operation. And this is what you apply to the system. So the overall displacement is going to be the sum of the red and green vectors. So this purple displacement. And modulo the stabilizer group, this turns out to be a logical X operation. So in this case, we ended up with an error by doing this decoding strategy. Now you can think about sort of which original displacements, Y, don't lead to an error for a given decoder. And what you find is that this is given by this blue region. So you take the Voronoi cell and you displace it by lattice vectors of the lattice L. And as long as the original error, this original displacement y, belongs to this blue set, you don't get a decoding error. And so once you have this, you can compute probabilities of correctly decoding. So for example, if the noise is Gaussian noise with variance sigma squared, then you see that as long as the variance is small compared to the volume of this, or the size of this Voronoi cell, then with high probability, you actually correct this error. Okay, so this should hopefully give you some intuition about what we're going to do next. Okay, so now I'm going to talk about encoding oscillators into oscillators, and this was proposed by No, Gerwin, and Jiang last year. And the procedure is as follows. You start with k bosonic modes that you would like to encode into n bosonic modes, and what you're going to use are certain GKP states. So these are states corresponding to a one-dimensional GKP code. So these are sort of canonical GKP states. And then you're going to sort of entangle these ancilla modes with these logical modes using a Gaussian unitary given by a symplectic matrix S. So that's the encoding operation. It's a Gaussian unitary. And then because you know the stabilizer generators of these states, you also know what the stabilizer operators are for encoded states. So decoding proceeds very similar as before. So let's again assume IID noise, displacement noise on every mode. And this gives you an overall displacement distributed according to a Gaussian. And so at this point, so after the error, you're going to measure the stabilizer generators, which again corresponds to measuring the exponents, if you like, and you get some syndrome. And we're going to again use maximum likelihood decoding for this error y to decode. So we're going to compute this and take minus that vector and apply the corresponding displacement. So that's the decoding strategy, and maybe you're wondering why we should use this kind of encoding. The whole motivation for this is that perhaps these codes are better than just Gaussian, just using Gaussian operations only. So here you're using these GKP states, which are non-Gaussian resource, and therefore this might go around certain no-go results we have for error correction using purely Gaussian operations and states. What we focus on in our work is basically asking whether this actually works in the sense of getting a threshold. And the worry here is that perhaps this Gaussian unitary, to actually make it work, needs to have a lot of squeezing. So in fact, if you think about symplectic operations, it's well known that you cannot deform sort of areas in phase space arbitrarily, but this is highly constrained somehow. One such famous statement is this no squeezing theorem by Gromov, which basically says that if you start with a ball of radius r, you cannot embed it into a cylinder with respect to the first symplectic coordinate of radius less than r. So operations are highly constrained, and if you further assume that we're in symplectic have a finite amount of squeezing, then it's going to be even more constrained. So squeezing we're going to quantify by the maximal symplectic eigenvalue of such a matrix. Okay, so now I can state our main result. So basically we're considering this setup with Gaussian noise of variance c squared on each mode. And this is equivalent if you use this decoding strategy to some logical displacement channel, which basically applies a displacement with some distribution x. So the question, of course, is what is the variance sort of this random variable x, or how it is distributed? And to quantify this, we use the following quantity. We just ask what is the probability that the norm of this vector is less than some given epsilon. And the main result we find is that this quantity is upper bounded by the probability mass under a standard Gaussian of a ball of radius epsilon times the squeezing of the symplectic matrix divided by sigma. So what this means is that basically to make this right-hand side close to 1, you need an amount of squeezing which grows as 1 over epsilon. Okay, so in particular, you cannot make epsilon arbitrarily small without using encoding unitaries that use a lot of squeezing. Okay, I think, am I almost out of time? So I will just...
4 minutes. 4 minutes.
4 minutes, okay. So let me just maybe mention how we can relate this to a classical estimation problem. This problem we call partial informed unwrapping of modulo reduced Gaussian vectors. We didn't come up with this name. It seems a bit awkward to me, but we only came up with the partial, so that the rest already existed. So the problem is as follows. So let me first introduce some notation. So for vectors in Rn, we call xa the first k components and xb the second n minus k components. And x star b is going to be the modulo reduced second part. So every component is taken modulo some constant delta. And now the estimation problem is the following. So x is a sample of an n-dimensional random vector with covariance matrix sigma that's known to everyone. This is why it's called informed. But now you're not given x, but you're only given this modulo reduced second part of x. And your task is to estimate this first part, xa. So you have to output an estimate. Now, one natural strategy here is just to use this second part and try to first estimate the whole vector. And once you have this, so you can do this, it's sort of a maximum likelihood strategy, and then you can just output the first components. So this is one strategy for this problem, and this is the strategy we consider. Because if you use this estimation strategy, it's exactly the same as this quantum problem that I described. So this is the quantum quantity we're interested in, and it can be related to this estimate being epsilon close to the actual value of this vector. Okay, so this reduces the problem to a classical estimation problem. And if you analyze this, you find that it takes a very similar form as what we had before. So there's something like a Voronoi cell that's displaced along directions of a lattice. And in addition, there's some parameter epsilon, which sort of enlarges these sets. So this is the Minkowski sum. So geometrically, this looks very similar, except that this is not really sort of a standard Voronoi cell. It's degenerate in a certain sense, and this lattice is lower dimensional, it's not full dimensional. So let me just end with some pictures. So this is what sort of this degenerate Voronoi cell looks like. It's bounded by uncountably many hyperplanes. Alternatively, you can think of it as being bounded by sets that have a boundary, which is a sort of quadratic surface, quadratic forms. And basically, we have to integrate over these Voronoi cells, and this is a little bit awkward. So what we do is we just replace this degenerate Voronoi cell by a polytope which contains it. And this polytope has a dimension n minus k. And then we have to also sum over displacements. So we can give an upper bound on this quantity, which is expressed in terms of the probability mass under the conditional distribution of xa given certain values of xb of certain balls of radius epsilon. And these quantities you can upper bound just using a Gaussian that has covariance matrix given by the Schur complement, because that corresponds to this conditional distribution. And you can also put this ball at the origin by Anderson's inequality. So in the end, you can relate everything to the eigenvalues of this Schur complement, and this we can relate to the matrix itself using a variant of Weil's inequalities, and in this way we can relate it to the squeezing. Okay, so this is basically what we found. So if you want to use these oscillator-to-oscillator codes to get a threshold, you need an unbounded amount of squeezing. So this is perhaps not physically so useful, but if you just want to reduce the variance, you can indeed do this as shown by no Gerwin and Jiang, you can just not get this asymptotic result because that needs a little squeezing. So thank you for your attention. I hope the audio quality was acceptable.